Hello, everyone. We continue our discussion of statistical analysis and inference today by looking into a new technique, hypothesis testing. Before we get to hypothesis testing, let's look at an example. Suppose I have a new teaching method that I want to test it for a particular course. And let's say I train 100 students using this new technique, and I test them and they receive an average score of 73. From historical data, we know that the students in this course have had an average score of 70 with a standard deviation of 10. Now, the questions that we would like to answer are as follows. Do you think the new teaching method is effective? Do you think the fact that the sample of 100 students received 73 as an average, as opposed to the historically average of 70, which all the students have been getting, is this a significant result? Should I use this result to conclude that the new teaching technique is more effective than the old ones? So to answer this question, we're basically comparing two hypotheses. One hypothesis says the new method has no effect. It's no better or worse than the old technique, meaning that if we test it on the entire population, the average score will still be 70. The other alternative states the opposite. No, the new technique is actually effective. And if we test it on the entire population, the performance is expected to improve. So we expect the average score of the entire population of students increase beyond 70. How do we test this? Let's assume that H0, the first hypothesis that says the new teaching technique is not more effective than the old one, let's assume that this is true. If this is true, I take a sample of 100 students off a population, and what I'm interested in, so this is my entire population, and I have an average score of mu. I take a sample, and this sample of 100 students has an average score. I show it as y bar. So mu is my population parameter, and y bar is my sample statistic. If this new teaching technique is the same as the old ones, basically means that nothing has changed about my sample statistic. So the sample statistic should be the same as before, meaning that it's an unbiased estimator and it will be normally distributed. And let's say I get a mean of 70 as I do. This is my y bar. This is my f of y bar, the distribution of that sample. So if the new teaching technique is not better, I do expect to get this, what I have been getting in the past. Now, however, I have got 73. So what I want to do is this. To test that hypothesis, I would say, okay, if nothing has changed, this is my distribution. What is the probability of getting 73? If with this distribution, the probability of getting 73 is high, it basically means that, yeah, this distribution is correct. And if this distribution is correct, that means that the new teaching technique is pretty much the same as the old teaching technique. However, if the probability of getting 73 is very, very low, that indicates that maybe this distribution that I'm showing here is not valid. And if this is not valid, it would indicate that perhaps the new teaching technique is better than the old teaching techniques. And if I apply that technique, my distribution is going to change, perhaps something like this. So that's what I want to test. Now, I know that y bar, which is the sample mean, is normally distributed. It is unbiased, so it has a mean of mu, and it has a variance of sigma squared, sigma being the standard deviation of the population, divided by n, the number of samples. So this gives me a normal distribution of mean of 70 and standard deviation of 1, or variance of 1. Now, for that type of normal distribution, what is the probability of getting a y bar greater than 73? If I convert this to a standard variable, it would be the probability of z being greater than 73 minus the mean divided by the sigma. And that would be equal to 3. So that's the probability of z being greater than 3, which is about 1%. So what that means is, if the first hypothesis is true, if this new teaching technique is no better than the old one, I will have this particular distribution. And with that distribution, there's a very, very slim chance that I get an average score of higher than 73. So now that I have measured 73 as my average score in that sample of 100 students, this is a significant result. And it could indicate that H0 is not true. We can look at it visually again. Imagine this is my distribution and unbiased estimator, which means that the mean of the estimator is the same as the mean of the population. If the first hypothesis is true, if the new technique is the same as the old one, and let's say I take a sample of 100 students, test them with a new technique, and I get an average of 70, basically what I can assume is that H0, that hypothesis, is true, because I did expect to get 70, I did get 70, which means the new teaching technique is pretty much the same as the old one. If I get 71, that's farther away from 70, but close enough to lead me to believe that maybe that assumption of the new technique being the same as old technique, that's still reasonable. If I get 72, moving further away from the mean of 70, maybe it's still acceptable, but I start losing confidence in my original hypothesis. And in that case, if I get 73, which means that with my original assumption, there's only 1% chance that I would get 73, that might indicate that my original assumption is not true. My original assumption in that case was my first hypothesis, H of 0. So the more extreme results that you get, the more willing you're going to be to consider the fact that maybe your original assumptions are not correct. Now, in hypothesis testing, our objective is to take a sample from a population, and from the information that is included in that sample, make statistical decisions. For example, you have a medication and you want to know if it's better than the old medications. You run a clinical trial, and from that trial, you decide whether this medication is better than the previous ones. Or you want to decide whether you should call an election. What do? You run an exit poll. Notice that all the votes have not been counted yet, but from the exit poll, you try to see if your candidate will win the election. Or you want to see if a coin is fair, you toss it a few times. That would be your sample. From the data that you get from that sample, you then decide whether that coin is fair. Now, the general procedure that we do is as follows. We create a hypothesis related to a population parameter. Remember, in the previous example, population parameter was the average score of the entire students. Then we sample the population and compare what we have observed from the sample with what the hypothesis says. If they agree, we accept the hypothesis. If they disagree, we reject the hypothesis. Now, sometimes instead of saying we accept the hypothesis, we say we fail to reject it. Or another terminology that is sometimes used is we withhold judgment. So you either reject the hypothesis or you accept it or you fail to reject it. Now, what are the elements of a statistical test? First, we have a null hypothesis. We show this as H of 0. This is the hypothesis that is supposed to be tested. In the previous example, that hypothesis was the new teaching technique is the same as the old teaching technique. It's not better. Then we have another hypothesis known as alternative hypothesis, shown as H of A. We usually try to find support using the sample data for this hypothesis to see if we can accept or reject the null hypothesis. We, of course, have to have a test statistic. That's an estimator that comes from the sample. In the previous example, that test statistic was the average score of the sample of 100 students. And then we have to decide on a rejection region. If that test statistic falls in the rejection region, we will reject null hypothesis in the favor of alternative hypothesis. Now, before we look into a couple of examples, let's discuss errors. There are two types of errors associated with hypothesis testing. We call them type 1 error and type 2 error. Type 1 error is associated with a situation in which we reject the null hypothesis when it is in fact true. We assume that the new teaching technique is better than the old teaching technique when in reality it is not. Probability of this type of error is known as the significance level of the test. So we basically say that's the probability of type 1 error, which means we reject the null hypothesis when it is true. And that would be equal to the probability that your estimator falls in the rejection region. Imagine this is your distribution, and let's say you say rejection region. Remember in the previous example, I said, for example, 73 would be an extreme result. So maybe we say anything greater than 73 is the rejection region. And let's say you get 74, it is in the rejection region. You reject the null hypothesis where in fact it is true. That is known as type 1 error. And notice we show it as alpha, which actually goes back to that notion of 1 minus alpha that we discussed during interval estimates. If you recall, we had a probability that this theta is between an upper bound and lower bound. We say that's 1 minus alpha. And I mentioned that alpha would be like 1%, 2%, 5%, 10%, those kinds of numbers. And this, in fact, is the type 1 error. That's basically the risk we are willing to take when we reject H0. That means when we reject H0, we may be wrong by a probability of 5%. That's the risk that I'm willing to take, meaning that if I reject H0, I am 95% sure that I made the right decision, but of course, 5% is a chance that I'm wrong. There is another opposite type of error. We call it type 2 error, and that is if we accept H0 when in fact alternative hypothesis is true. So we show that as beta, and basically is probability of accepting H0, null hypothesis, when the alternative is true, meaning that what is the probability that the estimator is not in the rejection region? Let's say in that situation, I get a 71, it's not in the rejection region, and I think, okay, my null hypothesis is true. However, despite the fact that this is not in the rejection region, HA alternative hypothesis is true. So your test score, let's say in the previous example, is close to 70, and you assume that, okay, it is 70, I expected to get 70, so the new teaching technique is not better than the old teaching techniques, but in reality, maybe it's better. That's another type of error that we might make and is known as type 2 error. Now, obviously, both of these errors are undesired. In general, if your sample size is fixed, any attempt to decrease one type of error would actually result in an increase in the other type of error. The best way to decrease both types of error, meaning that you reduce the risk that you're exposed to, would be to increase the sample size. That's the best you can do. Okay. Now, the last thing we talk about before we get to some examples is the p-value. The value of the rejection region and that alpha that I discussed, it's kind of chosen in a subjective fashion by the designer. So there is really no particular scientific rule associated with it. So a lot of times what we do is instead of basically specifying whether you should accept or reject the hypothesis, we just provide the p-value. We provide the p-value and then we let the reader decide whether he or she wants to reject or accept the null hypothesis. P-value is basically the probability of obtaining a result equal to or more extreme than what you have already observed when h of 0 is true. In that example that I had, remember, it was, a normal distribution with a mean of 70, and then I had a average score in my sample of 73, and the associated probability, if I remember it correctly, it was something in the range of 0.013. That 0.013, that's the p-value for that particular test, which says that if the null hypothesis is true, the probability of you getting 73 or anything above that would be 1%. And what we usually do is we choose a value for alpha, which is kind of standard, like 1% or 5%, and then calculate the p-value. If the p-value is less than alpha, you reject the null hypothesis. But if it's greater than alpha, you cannot reject it, or perhaps you can accept the null hypothesis. All right. Let's look at the formulation, and then we're going to have a couple of examples to see how something like this is applied in practice. First, we talk about large sample tests. When the sample size is large, as we have seen before, the estimator will have a normal distribution. So my theta hat, which is the sample statistic, my estimator, would have a mean of theta and its own variance. Now, what we do is I define my two hypotheses. One is my null hypothesis that says theta, which is my population parameter, is going to be some value, theta 0. The other alternative hypothesis would be no, theta is not equal to theta 0. In fact, theta is greater than theta 0, or less than, for that matter. And then we choose an alpha level test, which is the significance level of the test, and define the rejection region based on that value. From our discussion from interval estimates, you remember that if I choose my alpha, the probability that I am within this range would be 1 minus alpha theta 0. So theta hat is greater than theta 0 plus z of alpha times standard deviation of theta hat. And then I can standardize this random variable and say if theta hat is greater than this value, theta hat minus theta 0 divided by standard deviation is greater than z of alpha, meaning that z is greater than z of alpha. That's my rejection region. So if my value becomes larger than z of alpha, I would reject the null hypothesis. Now, as I mentioned before, these values are all standardized, meaning that we don't go with random numbers. We usually go with an alpha of 0.1, meaning that we're willing to take 10% risk, but we want to be 90% sure. Or 0.05, we're willing to take a 5% risk, but we want to be 95% sure. Or an alpha of 1%, or 0.5%, or 0.2%. And associated to each one, and these are values that you can see from hypothesis test tables or from normal distribution tables, in which provide you with those critical values. These critical values, remember that they indicate the range of your rejection region. If the value lies in one of those regions, you reject the null hypothesis. So what we do is as follows. We always have one null hypothesis, which in this case, for example, theta is equal to theta 0. And then alternative says you can have an upper tail alternative hypothesis that says theta is greater than theta 0. You can have lower tail, which is theta is less than theta 0, or you can have a two-tail alternative. Theta is not equal to theta 0. And for the statistic, what we do is we measure the statistic from the sample. We compare it with what the null hypothesis expects to see, and then we normalize it based on the standard deviation of the statistic. And this will give us, so this value is going to be z of alpha, and then the rejection region would be, if z is greater than z of alpha, rejection region for upper tail, which would be here. So if this null hypothesis is true, getting a value in this shaded region is an extreme result. So you would reject the null hypothesis. If z is less than negative z of alpha, that's a lower tail rejection region. Again, if this distribution for null hypothesis is true, and you get a value somewhere here, which is smaller than negative z of alpha, that's a significant result, and you would be leaning towards rejecting h of 0. And if z is, or absolute value of z is greater than z of alpha over 2, that's a two-tailed test. That basically says, if this is the hypothesis, that's the null hypothesis. If I get extreme values any part of the distribution, that would be grounds for rejecting the null hypothesis. So as you can see, we can have one-tailed tests when we look at upper tail or lower tail or two-tailed. In one-tailed tests, we are interested in extreme values to one side of the mean. For example, if the new technique is much better than the old technique. In two-tailed tests, however, we're interested in extreme values on both sides. So if the new teaching technique is much better than the old teaching technique or much worse than the old teaching technique, if the new medication is much better than the old medication or much worse than the old medication. So depending on the type of problem that you have, you would need to decide whether an upper tail or a lower tail would be more appropriate. Okay. Now that we have talked about the mathematics behind hypothesis testing, let's go through a few examples. So in the first example, we're looking at a manager that is claiming that salespeople are averaging no more than 15 sales contacts per week. And in order to check this claim, this manager selects 36 salespeople at random and records the number of sales contacts that they make every week. The mean and variance of contacts that are made by those salespeople are 17 and 9. So the manager claims that on average, they don't make more than 15 sales contact. When he or she looks into the sample data, notices a mean of 17 and 9. What we want to know is that this 17, that difference of 2 between 17 and 5, is it significant or can it be attributed to randomness? So does this evidence contradict the manager's claim? So what we do is this: we have to form the null hypothesis and the alternative hypothesis. The null hypothesis says the manager's claim is right. Mu is 15. So despite the fact that this sample of 36 salespeople is showing 17 sales contacts per week, the total population of all salespeople would still give me 15. So this is just a little bit off 15. The alternative hypothesis would be no. For the entire population, the average number of sales contacts that they make per week is actually greater than 15. Now, for this sample size, we can assume that the sample mean, y bar in that case, is normally distributed. We form a test statistic, which would be, again, remember, this is the first thing that you always have to do. You calculate the standard variable, which would be the sample mean minus the population mean divided by the standard deviation of the sample mean. So that would be y bar minus mu, and the standard deviation of the sample mean would be sigma divided by square root of n. The rejection region, because we're looking at a test level of 0.05, the rejection region would be 1.64. How do you get this? Let me take you back to this table here. So we're looking at a one-tail test. For the level of significance 0.05, your z of alpha is going to be 1.645. So basically what we have is, if my standard variable is greater than 1.645, then I can reject the null hypothesis because it is an extreme value. In other words, look at it like this. You have a normal distribution, which is standard, and for 95%, you're looking at 1.64. If this z that you calculate falls somewhere here, that means that this is an extreme value. You can reject the null hypothesis and go with the alternative hypothesis. Let's go ahead and calculate that. So for the sample, we had a mean of 17 against what the manager thought would be the case, which was 15, divided by standard deviation of the sample, which is, remember, variance is 9, so standard deviation is 3, divided by root 36, which is a number of samples in that group of salespeople. And that is 4, which lies somewhere here. That means it is more extreme than my threshold of 1.64. So it lies in the rejection region, and we would reject the null hypothesis. Let's look at another example. Suppose a machine in a factory must be repaired if it produces more than 10% defective items in one day. In order to see whether or not we have to repair that machine, we take a sample of 100 items from all the production that day, and that sample of 100 items contains 15 items that are defective, so kind of 15%, as opposed to my threshold of 10%. My question would be, is 15% of that sample being defective, is it a significant result? Should I go ahead and stop that machine in order to be repaired or serviced? Now, the supervisor says that the machine must be repaired based on that 15%. We want to see if the sample evidence support that decision. All right. So if y, in this case, is the number of observed defective items, it is a binomial random variable. We can assume that this is normally distributed. So let's define P as in probability that a randomly selected item is defective for the entire population. Population here is all the items that that machine is producing in one day. What we want to do is this. We want to test the null hypothesis that says, don't panic, everything is fine. And for that machine, for all the items produced by that machine that day, we're still at 10%. Don't read too much into this 15%. Against an alternative hypothesis that says, no, this rate of defective items is in fact greater than 10% for the entire population of items produced by that machine. So we create the test statistic. In this case would be the number of defective items out of all the items that we had in that sample, which is 15% in this case. Remember, once you define your point estimator, you have to standardize it. So we say standardized value is p hat minus p divided by standard deviation, which would be 15% minus 10%. Standard deviation is square root of p times q divided by n. And if you recall from our previous lecture, when you don't have P and Q values for the entire population, you use the values for the sample. You approximate it that way. So I will say, or actually in this case, I take that back, because in this case, we do have that 10%. So 10% here, 90%, products are going to be okay. 0.1 times 0.9 divided by 100, and that will give you 1.65. Now, where does that 1.65 lie? Is it significant or not? So 1.65, let's say somewhere here. Now, for test level of 0.01, again, let's go back to what we had for 0.01 for a single tail test. The value of alpha, z of alpha, would be 2.33. So we come back here. We have a rejection region, which is anything greater than 2.33. Now, we have 1.67, so we are not in the rejection region, meaning that this result is not significant. The fact that a sample of 100 items had 15 defective items in it it does not mean that the machine is actually malfunctioning. This is a relatively normal result based on the sample that you have. So this does not support the decision of the supervisor, so the machine does not have to be stopped in order to be repaired. The last one we're going to talk about is another example, or suppose we have a psychological study to compare the reaction times of men and women to a particular stimulus. Now, in order to do that, we take random samples of 50 men and 50 women, and the results show that men on average had a response time of 3.6 seconds to that stimulus with a variance of 0.18. And for women, those numbers were 3.8 and variance of 0.14. Does this data provide sufficient evidence to suggest that there is, in fact, a difference between the mean reaction times of men and women? Okay. So here, we wish to test two hypotheses. One is the null hypothesis that says, no, there is no meaningful difference between the reaction times of men and women. And mu1, which is the mean reaction time for the entire population of men, equals mu2, the mean reaction time for the entire population of women, against an alternative hypothesis that says, no, these two are not equal. There is a difference between the mean reaction times of men and women. Notice this one is a two-tailed test. I'm not interested in one extreme, rather I'm interested in difference between reaction times either being larger for men or larger for women. So that's a two-tailed test here. Now, for my estimator, I look at, remember again, I have one sample for men, one sample for women. I find Y bar for the first one and Y bar for the second one. So my test statistic is the difference between the mean of the first sample and the mean of the second sample. So it's Y bar minus Y2, Y1 bar minus Y2 bar minus, this in fact is Y1 minus Y2. But if the, I'm sorry, not Y, mu1 minus mu2. If the null hypothesis is true, mu1 and mu2 would be 0, meaning that this would be 0. Normalized based on the standard deviation of y1 bar minus y2 bar. And again, if you go back to the previous lecture, you will see that the standard deviation is sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. We plug in the numbers because we don't know sigma 1 and sigma 2. We replace them with s1 and s2, the square root of 0.18 and square root of 0.14. So this would be my standard deviation. And then y1 bar minus y2 bar is essentially 3.6 minus 3.8 minus that 0, which is mu1 minus mu2. That is minus 2.5. If I'm using a significance level of 0.05, the rejection region would be 1.96. Let me take you back again to this table. Notice that this is a two-tailed test. So for 0.05 level of significance, we're looking at plus minus 1.96. If the value is greater than 1.96 or less than minus 1.96, it would be in the rejection region. It is in fact minus 2.5, which is smaller than minus 1.96. So if this is minus 1.96, we are getting a value somewhere here, which is an extreme value, a significant value, which indicates that there is enough evidence based on this data to suggest that the mean reaction times for this particular stimulus would differ between men and women. Now, in the previous examples, I assumed that I have large samples. What happens if I have small sample tests? The essence of the study would be the same. So you still would have to have the same, form of null hypothesis and alternative hypothesis, and form a test statistic. But once you form the test statistic, which in this case is going to be your y bar minus mu0 divided by the standard deviation of your test statistic, this actually is no longer normal. If your population is a small sample, you're going to have a t distribution. So this will be t distribution with n minus 1 degrees of freedom. The way you would approach this problem is exactly the same as before. Again, you would have to decide on your alpha, which is the significance level of the test. And from, statistics tables, you will find what the thresholds are for the rejection region. Again, the shape of this is going to be pretty similar to normal distribution. So that will give you, for that alpha that you have, for example, what is T of alpha? This is supposed to be an alpha. So the approach would be the same. Let's talk about variance of populations as well. Imagine I'm having a random sample, size n, from a normal distribution with mean of mu. And the sample has a variance of s squared. Now, I want to make conclusions about the variance of the population. So population had some variance of sigma squared. I took a sample, I got s squared, and I want to know whether based on this s squared, I can make a conclusion or statistical inference about the variance of the population. Here again, I would do the same thing. My null hypothesis would be, let's say the variance of the population is some number, whatever your hypothesis is. And then alternative could be upper tail that says no, it's actually greater than that number, lower tail that says no, it's less than that number, or two tail, which says, well, it can be greater or smaller than that number, but it's not equal to it. In this case, again, as we saw before, your test statistic, instead of looking at s squared, because it's not easy to find a distribution function for it, we multiply it by the degrees of freedom n minus 1 divided by sigma 0 squared. And we know that this is going to be chi-squared distributed with n minus 1 degrees of freedom. And again, similar to before, you decide on the level of the test, your alpha. Once you decide on the level of the test, you can find what your x of alpha is going to be. If it's lower tail, if it's upper tail, it's going to be, your distribution, like what is the extreme value. If you have lower tail, what is, extreme value here, or it could be two tail. And you find whether your observation lies in that rejection region or not. Again, the exact same thing as we had before. Let's look at it through an example. A company produces machine engine parts that are supposed to have a diameter variance of no longer than so many inches. You take a random sample of 10 parts, and those random samples have a variance of 0.0003. Now, at the 5% level, which is alpha equals to 0.05, we want to test whether the variance of the total population is at this value, or are we making a mistake that based on this sample, we should assume that for the whole entire population, the variance is higher than 0.002. So what is my null hypothesis? Variance of the entire population is 0.002. Alternative says, no, based on this measurement that I had from a sample of 10 parts, I'm assuming that maybe the variance of the entire population is in fact greater than 0.0002. We form this test statistic, n minus 1, 10 minus 1 times s squared, which is your variance here, divided by sigma squared. Now for sigma squared, you can assume 0.002, and that value is 13.5. Now, when you want to choose the rejection region for a chi-square distribution, you need both alpha and degrees of freedom. So degrees of freedom are n minus 1. For n minus 1, which is 9 degrees of freedom, and an alpha of 0.05, the rejection region is anything greater than 16.19. If you are greater than that, you can reject the null hypothesis. But we're not. So, here that would be your 16.19. We lie somewhere here, 13.5, and this would be the rejection region. So this is not a significant result, and meaning that based on this data from the sample, we don't have enough evidence to assume that for the entire machine, the variance exceeds that value of 0.0002. The last test that we're going to talk about is when you want to compare two population variances. Here, imagine you have two random samples from two populations. One is size N1, one is size N2. And you basically want to know, based on what you find there, do the populations have the same variance, or, for example, the first one has a larger variance? Notice here, I'm looking at a one-tailed test. You could make it a two-tailed test and say, sigma 1 squared is not equal to sigma 2 squared. The test statistic that I form here would be the empirical variance of the first sample, S1 squared, divided by S2 squared. And then for, the level of alpha that you choose, you find the corresponding F of alpha, which would tell you what the rejection region is going to be. You calculate this. If it's greater than F of alpha, that means it's in the rejection region and you can reject the null hypothesis. Just like in the previous example in which we needed both alpha and degrees of freedom, notice that here we need alpha, we need degrees of freedom for the numerator, degrees of freedom for the denominator. So when you go to the F table, you choose the degrees of freedom for the numerator, for the denominator, and the alpha. From all those three values of this, and this, you will find your F of alpha, calculate this. If it's greater than that, you can reject the null hypothesis. So we're going to stop here for today. And again, a list of references, especially references 1 and 2, that will give you more examples of tests of hypothesis and how these different techniques that we talked about can be applied to various problems.